Okay, today we will continue on the soil solution chapter. Probably today we will finish this chapter. I hope you are keeping up and studying because things will accumulate too much. So please study your lectures and your book. Ion activity and activity coefficients. Thermodynamic equilibrium constants are expressed in terms of activities, not concentrations. We have already seen that in the last lecture. If you remember, we differentiated between thermodynamic equilibrium constant and conditional constants. Unfortunately, the activities of ions in solutions generally cannot be measured directly as opposed to their concentration. Concentrations we can determine using analytical procedures, but the activities, something we cannot determine in the laboratory. So we have to do something about it and we have to be able to calculate it. So we will see how we calculate it. So the activity and concentration of an ion in solution can be related, however, through the expression. The activity of B, any ion, equals the concentration of B times gamma of B. We will know what gamma of B in a minute, where B in brackets is the concentration of species B in moles per liter, and gamma of B is the single ion activity coefficient for species B. Species B means any ion in salt solution, cation, anion, it doesn't matter, any ion in salt solution. So we can do it for all the ions that are in salt solution. So this gamma of B is the single ion activity coefficient for that species. The single ion activity coefficients are typically calculated using the extended to account for the effective size of hydrated ions Debye-Huckel equation. Debye-Huckel equation. We look at this equation, the Debye-Huckel equation. Log gamma of I, just a minute ago we said of B, species B, I is another way of saying any species, any ion we're interested in the salt solution. So log gamma of I equals minus, remember, never forget this sign, minus A Z I square, open big parenthesis, I to the half, well, that means the square root of I, over 1 plus B, A sub I, small a sub I to the half, which is again the same. We will know what all of these symbols are. A has a value of 0.5 at 298 Kelvin, 298 Kelvin, the degrees in Kelvin, and related to the dielectric constant of water. So this is pretty much constant. So you should know it. You should remember this. This will not be given to you in the exams. A, you have to know the value of it is 0.5. B has a value of about 0.33 at 298 Kelvin. And also, so there is an O here missing, also related to the dielectric constant of water. So B also has a value of 0.33. You should know. This will not be given to you in exams. A sub I is a parameter corresponding to size in angstrom, A angstrom of the ion. So, sorry, A sub I, this has to be the size in angstrom. Angstrom, we will find out that in your book, the tables, they are given in nanometer. The angstrom is 10 to the minus 10 of a meter, and nanometer is 10 to the minus 9. So always, if you are given the A sub I for that ion, the size for that ion, this parameter, if it was given to you in nanometer, you have always to change it to angstrom before you plug it in this equation, in the Debye-Hackel equation. So this has to be in angstroms. Remember, A sub I is a parameter corresponding to size, the value of it in angstrom. Okay, so the ionic strength is related to the total electrolyte concentration in solution and is a measure of the degree of interaction between ions in solution, which in turn, which will happen after that, something will happen because of that, which in turn influences the activity of ions in solution. So the ions in solution, the more there are ions, the more they will interact, whether positive, negative, they affect each other. So this term, which is we call the ionic strength, is related to the total electrolyte concentration in a solution, and it measures the degree of interaction between these ions. So the concentration of all these ions in solution will affect their interaction. The more they are there, the more interaction. The less ions there are there, the less will be the interaction. We will know how to calculate this in a minute. So how do we calculate the ionic strength I equals half summation of over I. That means over I, you have learned this in math. This summation over, if you have, say, 10 ions, you add up all these terms for the 10 ions. If you have 5 ions, you do this for the 5 ions, and so on. So over I, that means over all the ions that are in the salt solution you're interested in. So remember, there is half, always remember this half, and then you summation of Ci Zi squared. So I is the ionic strength, Ci is the concentration in mole per liter of the ith species. Again, ith species, that means the first, the second, third, all the ions, you put them side by side and you start with the first one and then you go to the next and so on. So that's what the meaning of the ith species or ion. Zi is the charge or valence of the ith species. So this is the concentration of that ion, okay, in mole per liter. And then Zi is the charge. Because it's square, it doesn't make any difference, which you still have to show so that you don't make mistakes, negative or positive, but you put it between parentheses. We will see how we calculate it also. And when you square it, then you don't see the sign, it becomes all positive. E, like I have said, extends over all ions in solution. We will see examples. Let's look at some examples how we calculate the ionic strength. Example 1, you have a solution of 0.2 molar sodium chloride, 0.2 molar. When this dissolves, it gives you Na plus Cl minus. So if you have the concentration of the salt 0.2 molar, it will give you 0.2 molar of sodium ion plus 0.2 moles per liter of molar chloride ions. So remember, equal 0.2 moles of this and moles of this per liter. So I equals, remember, we put the half, summation of Ci Zi square. So half, open larger parentheses, between parentheses, we'll start with sodium. 0.2 is the Ci, remember, the concentration of sodium. Remember, close the parentheses, plus 1, which is the valence of sodium. Close these parentheses, you square it. Plus, because so this is the first ion, sodium, plus, you open parentheses. The opening the parentheses and closing is extremely important, where you don't make mistakes with the addition and multiplication. Okay, so you have 0.2 molar, we said, for chloride. Chloride is -1, between parentheses, square. So you add up and this becomes, you add them up, it becomes 0.2 mole per liter. So I, for this solution, 0.2 molar NaCl, the ionic strength for that is 0.2 mole per liter. Remember, never forget about the units. You cannot have a number without unit. Units are important. In an exam, if you write just this, without this, you take only 50% of your grade. So remember, any number has to have a unit after it. Example 2, let's take another example. The same concentration, 0.2 molar, but this time of calcium chloride. Remember, when calcium chloride dissolves, it will give us Ca2+, it has two valences, two positive valence, and plus 2 Cl-, 2 chloride ions, 2. So the concentration of calcium will be 0.2 mole per liter, but the chloride, it gives us 2. So the molarity of it will be 0.4. Okay, but 2 ions for each molecule. Okay, so 1 mole gives us 2 moles of this. 0.2 mole gives us 0.4 moles of chloride. So again, we put the same equation. Half summation of Ci squared equals 1/2. Don't forget the half. You open big parentheses, open inside parentheses, 0.2 mole per liter for calcium. Multiply it by +2, which is the valence of calcium, divalent, +2, close the parentheses, square, plus 0.4, which is the concentration chloride. We remember it gives us 2 chloride ions, so 0.4, open parentheses, -1, which is the valence of chloride, close it, square. So this will give us 0.6 mole per liter. Look at the same original concentration as for the salt, 0.2 molar sodium chloride gave us an I equals 0.2 mole per liter, while the same concentration of calcium chloride, 0.2 molar, gave us an I of 0.6 mole per liter, much higher, because the interaction more, here we have more ions and we have higher valences, so the interaction between the ions is more in this case. So that's why I reflects the interaction between the ions in salt solution. Now, how do we go back to the single ion activity coefficient? Remember, to be able to calculate the activity, we need to calculate gamma, which is the single ion activity coefficient. And we said we use the Debye-Huckel equation. We have already seen it. Let's take an example. Again, remember, there is always minus AZI squared, big parenthesis. And this, you have the fraction I to the half, square root of I, which we know how to calculate now, over 1 plus B, capital B, A sub I. This, you will be given that I to the half. Okay, so let's take the example. Calculate gamma for calcium at 298 K when I equals 0.02 mole per liter. So now you are given I. This is the value of I. You don't have to calculate it. Sometime in the exams, I will give you a solution, just like I have shown you on the previous slide. I will give you a solution of certain concentration, and you have to calculate the I. In this case, it's given to you. It's a value that's given, so you don't have to do any calculation of I. The value of I, 0.02 mole per liter. A sub I, sorry, for calcium from table 4.5, page 125 in your book is 0.60 nanometer. All the values that are given in your book in that table are in nanometer. So you change it to angstrom. The angstrom is smaller, 10 to the minus 10 of a meter. Nanometer, 10 to the minus 9. So you multiply this by 10 to becomes 6 angstrom. That's what you use here in this. Always, this has to be in angstrom. So again, log gamma of calcium equals minus, we said this one, you should know the value of it, 0.5. Okay, Zi for calcium, 2, the valence is 2, square. You open the big brackets, then I to the half 0.02, the value given, to the half, the square root 0.02 over 1 plus 0.33. Again, the value of b you should know. It's always not given to you. Times 6, which is a sub I. We calculated it in angstrom. Times, again, I to the half, 0.02 to the half. It's best when you do this type of calculation, do it in steps like I have done. Calculate, sorry, calculate each one of them alone. Like this, find the value of this, find the value of this, find the value of this fraction, then multiply. Don't do it in one step. If you do it in one step and you make a mistake, that's it. This way you will see how easy to go from one step to the next and your mistakes will be less. Again, log gamma of calcium equals -2, 4 times 0.5, -2, you open parentheses, this value will be 0.144, and this, when you add 1 plus 0.33 times this, over 1.280. So remember, never forget this negative sign. So minus 0.2209, that's the log. Now we want to find the gamma. You get the antilog of this number. The antilog of this number will be the gamma from your calculator. You get 0.6013, 0.6013. Again, when you get numbers like that, don't say, well, it's approximate. Some you will say approximately 0.6. Why approximately 0.6? But also you don't want to put here 10 figures because the calculator gave you 10 figures. You have to be reasonable. Go with the significant figures that are given. And these numbers, we need to be at least to 3 decimal figures. If you say 0.601, that's fine. But don't say around 0.6 and ignore these. That's not good enough. You should be accurate enough in these small numbers and give at least 3 significant figures in these small numbers. Go over the values and do the calculation yourself so that you practice. And you take another example from your book. Take any of the ions and you know the value of A. Give yourself any I, different I. Go through the calculation, carry out the calculation so you know how to do it in the exams. Okay, the extended Debye-Hackl equation, the one we just called extended, it has the A sub I, which is the parameter that's related to the size. The extended Debye-Hackl equation is one of several equations that have been derived to account for ion-to-ion interactions in aqueous solution. Single ion activity coefficients calculated using the extended Debye-Hackl equation begin to deviate from actual measurements. However, when the ionic strength of the salt solution is greater than 0.2 mole per liter. So the more concentrated solutions, we cannot apply. Deviate, that means change from the real values. It doesn't give you the real values. It gets away from the real values. So you cannot use it for concentrated solution. Any solution, if I give you any solution that's greater than 0.2 mole per liter, its total concentration, the I is more than that, then you cannot use this equation. For more concentrated solution, we start using different equations. There are many, but at least we'll go over one. I less than 0.5 mole per liter, greater than 2, remember, greater than 0.2, but it has to be also less than 0.5 mole per liter to use this equation, which we call the Davies equation, not Davis, Davies, I-E-S, Davies equation. And this is given as log gamma I, remember, log gamma I, the same like that, minus AZI squared. This is similar, but inside is different. I to the half over 1 plus I to the half. Remember, this whole fraction you subtract from it, not you subtract from the top part. No, you subtract from the result of this fraction minus 0.3i. So you should know this Davies equation. If I give you, say, an ionic strength, if I ask you to calculate the single ion activity coefficient for an ion in a solution with I greater than 0.2 and less than 0.5, that means you have to use this equation, Davies equation, not the Debye-Huckel equation we talked about earlier. Okay, we'll move on to another aspect, which is extremely important, the solution and solubility processes that take place in the soil system. The solution is the dissolving of a soil solid. You know that. The solution, dissolve, the solution, dissolving. So a solid, a compound, it dissolves, that's the solution. Precipitation is the process of depositing a substance from the soil solution. So the ions, when they get back together, they get together back again to form a solid, to form a compound. It precipitates. So the solution, a compound dissolves into ions. When ions get together again to form a compound, they precipitate. That compound is precipitated. These are the chemical reactions that determine the fate of inorganic mineral components in soils. This is extremely important because which compounds precipitate, it'll take away many of the ions that are there. And if the compound has very high solubility, it dissolves again, giving you the ions again. So that's why it determines the fate of what's happening. What are the inorganic mineral components that we find in soils, in the soil solution? Soil formation, weathering processes, and contaminant mobility are all affected, of course. Soil formation processes, remember when we talked about clay minerals, how they form from a pool of so many ions together, then the secondary minerals start forming. The weathering processes that will result into all kinds of different new compounds, new ions, it's all related. And contaminant mobility, the contaminant, how fast they move. If they are ionic form, they will move, of course, with the water, with the salt solution downward. If they precipitate, they become stable, they stay in the soil, and so on. Precipitation of minerals occurs only when supersaturation conditions exist in the soil solution. We'll talk about this supersaturation and undersaturation in a minute more. So precipitation, when you have a solution and it got to be supersaturated relative or related to that specific compound we're interested in, that compound will start precipitating. And if we have undersaturation, then the dissolution will take place. We will see that in more detail in a minute. Okay, let's get back again to the thermodynamic dissolution constant, thermodynamic equilibria, but this time we're interested in the dissolution reaction. So we call it dissolution constant, but it's again, it's an equilibrium constant, thermodynamic equilibrium constant, but it is specific for dissolution. So we call it the dissolution reaction of the solid. We take any solid, MaLb, MaLb to be, this is cation and ion, you know, and these are the stoichiometric numbers to make this as a compound. Okay, this is, remember, in reversal process. Okay, so you have A of M, the valence of its M plus B of L, the ligand or the negative, and the negative, the charge of it is L minus, and it's aqueous to indicate we're talking about ions in an aqueous solution. Let's take, say, if we take gypsum for as an example, CaSO4. Remember, gypsum is CaSO4 0.2 H2O, but because we're interested only in the ions, we ignored the 2 H2O because it's water and it's an aqueous system. It's not going to change anything. That's why we wrote it this way. But if you're asked to write the formula of gypsum, you say CaSO4 0.2 H2O. It has water, 2 molecules of water of hydration. So it gives you calcium ions. Remember, these parentheses means activity. times sulfate activity. The thermodynamic dissolution constant, K0, thermodynamic, remember, we refer to it as K0 of dissociation for this reaction is you multiply the activity of calcium times the activity of sodium sulfate over the activity of calcium sulfate. The activity of calcium sulfate as a compound or of any other pure solid phase is defined as 1. By definition, chemists defined the activity of pure compounds as 1. So this will go divide by 1. That means we remove it. The activity of calcium sulfate of any pure solid. Here, pure, it doesn't mean pure from things around it, so things mixed with. No, we talk about the structural purity. That means the structure of it, all the ions in it are only calcium and sulfate, no other substitutions within the structure of the mineral itself. That's what purity in this case means. So the activity of calcium sulfate or any other is 1. So K0 of the solution, when we put this 1, it becomes calcium activity times sulfate activity equals K0 of SO. SO, remember here we call it the solution constant. Also, we call this the thermodynamic solubility product constant because it's now became only solubility product of the two activities. That's why we call it, but it's the same number. It's the numerically, it's the same. We're talking about the same thing, but naming slightly different because we removed this one. So it became the multiplication of the activities of calcium and sulfate. So the thermodynamic solubility product constant and is numerically in number equal to K0 of the solution, which is here. When the solid phase is pure, there are no structural imperfections. I already talked to you about that. So calcium activity times sulfate activity is often referred to as the ion activity product, IAP, the ion activity product, because it is like, remember, K of the solution and also the thermodynamic solubility product, the same. But to reduce it, because we are multiplying only ion activities by themselves, it's also called the ion activity product. And we'll know why. It helps us to understand the solubility of these compounds. IAP, ion activity product. And together with the K0 of SO is an index of whether the salt solution is in equilibrium with a given inorganic mineral component. Again, we'll see how do we test that. How can we check using that to see if we have the equilibrium or not. So we'll use the ion activity product that we already seen how we use it. If you take same general compound MALB and you write down just like we did before, the ion activity product for this compound is defined as M, which has valence of M plus, to the A times L, which has a negative charge of L minus, raised to the power B. So for gypsum, we already seen that IAP will be calcium activity times sulfate activity. IAP can be applied regardless of whether the dissolution reaction is actually at equilibrium or not. So this can be used anytime you can find, if you are given a salt solution and you determine, remember, how do we get this activity? You remember, first, you get the concentration of calcium, and that we measure by analytical procedures in the laboratory. Okay, and then we, in that solution, we also decide what's I, the ionic strength. After we know the ion strength, we find gamma of calcium. After we find gamma of calcium, we multiply the concentration of calcium to find the activity of calcium. So remember those steps we already gone through. You have to do this for every ion you're dealing with. We do the same thing for sulfate. Then if you have the activity of calcium and the activity of sulfate, you multiply them by each other, then you get the ion activity product, IAP for calcium sulfate for gypsum. So this, you can do it for any ion. You can apply it whether you have equilibrium, you don't, we don't know. You can always find this IAP. But why do we that? What do we get out of that? IAP can be used for determining whether dissolution equilibrium actually has been achieved or not. If we have, do we have equilibrium? So we calculate what we call omega. This is a new term, omega. Omega equals IAP, which we calculate for any solution we have. You calculate CaSO4 from the analysis you do, divided by KSO. This is a thermodynamic in which we have, this is known value from thermodynamic and chemistry books. This is available value, unknown exact K for that particular compound. So IAP is for the solution we have. So we calculate IAP. And then somebody will ask us, are we going to have equilibrium in this particular solution we have? Or are we going to have undersaturation or supersaturation? So we'll see. If omega is less than 1, look at this fraction. Omega equals IAP, ion activity product, over K. Okay, so if this is less than 1, that means this value is smaller than this value. IAP is smaller than K. So that means the solution did not reach the K. You need more ions to reach K, to reach equilibrium. So we say the solution is undersaturated. It did not get to the equilibrium. The concentration, we multiply these activities, did not give the value of K, so we do not have equilibrium. So this is undersaturated. We did not reach the saturation or the equilibrium point. If omega is greater than 1, you calculated this over this greater than 1, which means this product for that solution we have greater than K. So this cannot stay. It's oversaturated. Some of these ions have to get together and precipitate to form calcium sulfate to reduce this to K. So we have a supersaturated solution. And when a dissolution reaction is at equilibrium, gamma equals 1. If it's equilibrium, if this and this are equal, we have equilibrium. So we are not going to have dissolution. We're not going to have precipitation. If you have undersaturation, remember, undersaturation, that means this is not enough. We do not have enough to precipitate it. If you have supersaturated solution, that product, that compound will start precipitating to reduce the ions so that the multiplication of this will be equal to K. The last part of this will be the solubility diagrams. When studying the solubility of chemical elements in soil, we need to answer an important question. Does a solid phase control the concentration of a particular element in the soil solution? And if so, which solid phase is it? Okay, let me explain it again. So suppose you are going to study the solubility, say, of calcium, of phosphorus, of any ion that you're interested in soil solution. We can ask a question, is there a compound that is controlling the amount of that element in solution? If there is, which just like we have seen in the dissolution equations that we discussed, if there is, we need to know what is that solid phase? What is the compound that controls the concentration of that particular element? So we'll go through this procedure so that we see how we do this, how we determine this type. An answer to this question can be developed readily in terms of the dissolution equilibrium constant, K0 of dissolution. The method of analyzing the problem leads to the construction of what we call a stability diagram. We'll take an example, just an example so that you see how it's done. Gibbsite solubility. Gibbsite is AlOH3. Aluminum hydroxide is called gibbsite. So we'll take this an example. For this reaction, AlOH3 solid plus F3H plus, okay, back and forth, that means reversal equation, Al3 plus 3H2O. Okay, K of the solution for this, again, we can obtain from thermodynamic data from chemistry books. This is available. So in table 4.6, page 129 in your textbook, the value for this equation, for this reaction is log K. Remember, if you are given log K or K itself, you may remember this is the log of K, 8.04, okay? So if you write down K for this equilibrium, you write Al, sorry, 3, okay, Al3, in parentheses, the activity of aluminum over the activity of hydrogen cube. This water, pure liquids and pure compounds, remember, their activities are 1. So water is ignored, the activity is 1. And this, we assume, it's, remember, we said pure compound, no structural deficiencies in it. So the activity of it will be 1. So we're interested only in the ions. So that's why K becomes Al3 over H3 plus to the power 3 equals, we are given log K this, so K will be 10 to the 8.04. You know that, right? If you're given the log, the K itself is 10 to the power, same power. So take the logs of each side of this, take the log of this. So log Al, remember, and it will be minus 3 log H, concentration or activity, equals 8.04. Rearranging, remember, minus log hydrogen, we call it pH. Minus log H becomes pH. So the equation will be log of Al3 plus equals 8.04 minus 3 pH. The pH comes from the hydrogen concentration, minus 3, the concentration of hydrogen, so minus 3 pH. There are different ways. I'll discuss this and we will go back to that equation, how we construct the equilibrium. There are different ways of getting that K, the K value, that either it's obtained in the laboratory by measurement. Chemists know how to do that. If we have also the free energy information, we can also calculate that K for any reaction. The standard free energy of reaction and the equilibrium constant. You have studied this, I'm sure, somewhere in your chemistry. Delta G0, the standard free energy, delta G0 equals summation of delta G0 of formation of the product. This R for the reaction. R, delta G0 of the reaction, the standard free energy of the reaction, equals summation of, you add the delta G0 of formation of all the products, you subtract from the summation of delta G0 of formation of all the reactants. So delta G0 of formation is the standard free energy of formation. Again, this is available data. You cannot memorize it, it will be given to you. For reaction 7 in table 4.6, page 129 in your textbook, delta G0 of the reaction equals, just like we have done, you go through the products minus the, look at the products, look at the table, look at the numbers you have, and you can see where we get all these numbers from. I'm not going to go through each one of them. It's very simple mathematics. Remember, summation of the products minus the summation of the, you add all the standard free energy of formation of all the reactants subtracted from that of the product. So the big square, that's for the products minus the reactants. So, and the values here are given in kilojoule per mole, kilojoule per mole. So the answer we get for delta G0 of R minus 45.92 kilojoule per mole. The standard free energy change of a reaction is related to the equilibrium constant. Again, you have seen that, I'm sure, in your analytical chemistry or somewhere you should have already taken that. How we relate the K to the delta G0 of the reaction. So the standard free energy delta always, because we measure from one case to another. You don't have a standard value, absolute value of this. You always change from one condition to another. So we give it delta, the change of G0 for the reaction equals minus RT ln K0 of the dissolution. This is the one we're gonna calculate from this value this time. R is the universal gas constant, and T is the absolute temperature in Kelvin, absolute or Kelvin temperature. At 298.15 K, which is standard, what we call room temperature, 25 Celsius, delta G0 of reaction equals the value of this universal gas constants has different values. If we use the kilojoule, it has a certain value. In the old calculations, they used to use calories. This value will be different. So this is 0.00831 kilojoule per Kelvin per mole times the temperature. Remember, minus R, this is R, T, 298.15 K. We multiply by 2.303 log K0. Remember, here was ln, the natural log, to the base E. When changing from base E to base 10, remember, E is smaller. So the log will be a smaller number. So you need to multiply it by this factor. This factor is to change from ln to log. So that's why all these are constant. The universal gas constant is constant. Temperature is given, 298.1 is constant. This, to change from ln to log K, is also constant. You multiply them by each other. So log K0 of this solution equals minus delta G0 of R for the reaction over 5.71. So now we have this as a constant. Normally, you should know that. Most of the time in exams, I give you this, but it's easy to remember. This relationship between log K0 for any reaction equals minus delta G0 for that reaction, which we calculate from the standard values that we are given, okay, over 5.71. This constant came from these constants. All of these are constant, so this is the constant which is coming from these. So now we go back how to calculate standard free energy of reaction equilibrium constant for the reaction 7 in table 4.6, page 129. Sorry, log K0 of the solution, we calculated delta G, remember 0 for that. Remember, minus the value of it minus, so don't mix, don't forget the negative. The negative here is there in the equation. If we go back, so this negative, there is a negative sign, don't forget it. So this negative, and the value we calculated is negative. So minus, open parenthesis, minus 45.92 over, this is constant. So log K0 of this equals 8.04. which this is how we found log K, 8 over the same value we have given before. So the equation that, go back to the equation that we already derived, log AL 3 plus the activity of aluminum equals 8.04 minus 3 pH. So this is of the form Y equals A plus px. pH is changing. The concentration of aluminum is changing. This is a constant. This is a constant. So you have Y equals A, the intercept, remember, and this is the slope. B is the slope. So Y equals A plus bx. A plot of this relationship will give a straight line. That is the equation of a straight line. So if we draw that type of relationship, you put on the y-axis log aluminum activity and the pH. So after you draw this, we say we draw this from so many salt solution samples we collect, and we have this relationship, and you have a straight line relationship. Now, if I get a sample and read the pH of it, if I calculate and measure the pH of it, I say the pH 6. Immediately you say, okay, at pH 6, you go up and you find what is the activity of aluminum in that solution. So if Gibbsite, say, is the one controlling the activity of aluminum, then we measure the aluminum that we have in salt solution. And if we find it is the same value we obtained from measuring the pH and calculating it from this diagram, we compare it to the value we determined in the laboratory. We say Gibbsite is really the compound which is determining the concentration of aluminum in solution. In your book, what we do, suppose we know that there are 4, 5, 6 possible compounds that could control the concentration of aluminum in solution. So you do for each one of them this type of diagram, for each one of them, and then you draw them on the same diagram. So you have so many lines, and in your textbook there is an example, but I want to show you the idea. Then you measure, say, if they are related to the pH, you raise up and you see, okay, if this one is controlling the solubility of aluminum, the value will be this. If it is another line here, you read the value. If another one, you read it. You compare the value you obtain in the laboratory. You measure aluminum and you calculate its activity from that concentration measurement. Then you compare it. Which of these lines really gave you that value? Then you say, okay, that is the compound that controls the aluminum activity or solution, the amount of it in that solution. So this finishes this chapter. Next time, we will start a new chapter.